linear vector spaces. Associate Professor Cătălin Angelo Ioan from Danubius University, Galați, Romania. This is me, Cătălin Angelo Ioan. I have to go to Thailand. But first, I need to pack my bags. And also my dog, my cat, and my mouse. But not Microsoft mouse, a real mouse. Oh no, not this time. As far as I know, the weather is warm, so I'll have to prepare my luggage accordingly. Let's see what clothes I need each day. A clothes suit, a shirt, comfortable shoes, and a hat and sunglasses. Do not forget, I write on a paper. The structure of my clothes is therefore V equal clothes suit, shirt, shoes, hat and sunglasses. And since I do not need in one day only one piece of each, with the obvious exception of shoes, I will write synthetically V equal 1, 1, 2, 1. There are several things to note. V is in V. The elements of V are ordered sets in the sense that if we change between them, for example, components 3 and 4, we get a situation, let's say, weird. Oh, I forgot. I will not stay in Thailand for 1 day, but 5 days. Therefore, my luggage structure becomes 5V equal 5 multiplied by 1, 1, 2, 1 equals 5, 5, 10, 5. I think it's more convenient than V equal what you see on the screen. But what would happen if I were traveling an indefinite number of days, let's say alpha days? You have realized that in the previous example, I did not present to you the entire structure of my luggage. It is possible that, when traveling more, the rain will start. Therefore, let us note this with V equal V1, V2, Vn in V big, where n represents the number of distinct objects in my luggage and V the respective types, suits, shirts, etc. We have therefore defined above a first operation called external composition law, alpha V equal alpha V1, alpha V2, alpha Vn in V, where alpha belongs to R. My suitcases are not so large enough to be able to introduce so many objects. Therefore, I will take 2 suitcases and divide the objects as follows: 5, 5, 10, 5 equal 2, 3, 6, 1 plus 3, 2, 4, 4, where the first ordered set on the right represents the contents of the first suitcase and the second of the other suitcase. For an arbitrary structure V equal V1, V2, Vn in V and W equal W1, W2, Wn in V, we will define V plus W equal V1 plus W1, V2 plus W2, Vn plus Wn in V, and we will call this second operation the internal composition law, or the head of components. What have we got so far? A new set called n-dimensional arithmetic space Rn equal V1, V2, Vn, where V1, V2, Vn belongs to R, with 2 operations, alpha V equal alpha V1, alpha V2, alpha Vn in V, where alpha belongs to R, V v plus w equal v1 plus w1, v2 plus w2, vn plus wn in v for any v and w in v and alpha belongs to R. What properties do these two operations have? The head of order sets and tuples. 1. For any v and w in Rn, v plus w are in Rn, called the internal law. 2. V plus w plus z equal v plus w plus z. For any v, w, z are in belongs to Rn, the associativity. 3. There exists 0 with all components 0 belongs to Rn, such that v plus 0 equals 0 plus v equal v for any v in Rn, and 0 is called its null vector of Rn, the neutral element. 4. For any v equal v1, v2, vn in Rn, there exists v equal minus v1, minus v2, minus vn in Rn, such that v plus minus v equal minus v plus v equals 0, the opposite of v. And 5. For any v and w are in Rn, v plus w equal w plus v, the commutativity. So we can see that Rn plus is an abelian commutative group. What properties do these two operations have? The external multiplication of order sets. 1. For any v in Rn and for any alpha in R, alpha v is in Rn. 2. Alpha multiplied by v plus w equal alpha v plus alpha w for any vw in Rn and alpha in R. 3. Alpha plus b multiplied by v equal alpha v plus beta v for any v and alpha beta. And 4. Alpha beta multiplied by v equal alpha multiplied by beta v for any v and alpha beta. And 5. 1 multiplied by v equal v for any v in Rn. Can we generalize these notions? The answer is, as usual, yes. It's called linear vector space, a pair of two non-empty sets, vk, which elements are called vectors for v and scalars for k, and for operations plus defined by v multiplied by v with values in v, such that v with plus is an abelian group, plus defined by the Cartesian product k with values in k, where to the pair alpha beta corresponds alpha plus beta, and the multiply defined by k multiplied by k with values in k, alpha beta corresponds to alpha multiplied by beta, such that k with plus and the multiply is a field. And also an external operation denote also with multiply defined by the Cartesian product k multiplied by v with values in v, such that 1 alpha multiplied by v plus w equal alpha v plus alpha w, 2 alpha plus beta multiplied by v equal alpha v plus beta v, 3 alpha beta multiplied by v equal alpha multiplied by beta v, 4 1 k, where 1 is the neutral element for the multiplying in k, multiplied by v equal v for any v. we will note such a structure V over K, and we will say that V is a vector space over K. There is now an absolutely natural question. There are other vector spaces outside of Rn? The answer is again yes. Examples of vector spaces. The set of matrices M, Mn over R with M lines and N columns with the usual operations add and multiplying with scalars. 2. The set of polynomials Rx with real coefficients with the usual operations add and multiplying with real numbers. 3. The set of polynomials Rnx with real coefficients and degree less than or equal with n with the usual operations add and multiplying with real numbers. 4. The set of continuous functions fab equal the set of all functions f defined on AB with values in R, where f is continuous on AB, with usual operations add and multiplying with real numbers. 5. The set of derivable functions D over AB, open interval, equal f defined on AB with values in R, where f is derivable on AB, with usual operations add and multiplying with real numbers. 6. The set of integrable functions I from AB, closed interval, equal all functions f defined on AB with values in R, where f is integrable on AB, with the usual operations add and multiplying with real numbers. 7. Any field K is a vector space over itself, defining the addition of vectors as the addition on K and the multiplying with scalars as the multiplying on K. Therefore, we have that the rational numbers Q, the real numbers R, and the complex numbers C are vector spaces over themselves. Surprise! 8. Considering a set U with a single element U equal E, we will define the vector aiding as E plus E equal E, and the external multiplication alpha multiplied by E equal E for any alpha in K, where K is an arbitrary field R, C, Q, etc. U with these operations becomes a linear space over K. It is called the trivial linear space. So what? After all these considerations, any object in nature becomes a vector space. What is right? Trivial. For example, if U equal a man is a vector space with the operations the man plus the man equal the man, alpha multiplied by man equal man. Let us remind that a binary operation is nothing more than association of two elements to a third, not necessarily different. Finally, I am clear about these notions, so I can go to Thailand. But the weather in Thailand will be rainy. I have to give up a bunch of luggage: a clothes suit, a shirt, comfortable shoes, a hat and sunglasses. Now, the structure of my luggage is now U equal clothes suit, shirt, shoes, and 0. U satisfies all the axioms of vector space and is, in addition, included in V. We will call U a subspace of V, and we will denote U less than V. So what? The advantage of a subspace is that any property of the vector space is transmitted over it, but not vice versa, saving a precious time for reproofing some of its properties. I'm done with my departure to Thailand. Another problem now appears. We have seen that on a vector space we have two vector operations, adding them and multiplying them with scalars. What is the most general expression of these operations? On R, there are, for example, algebraic expressions, which are combinations of numbers with the add operations, the subtraction being a particular case of addition with the opposite number, and multiplication, the division being also a particular case of multiplication with the inverse of a number. In a vector space, the situation is similar. We call linear combination of n vectors V equal alpha 1 V1 plus alpha 2 V2 plus alpha n Vn for any V1 Vn in V and alpha 1 alpha n in K. It is good at something the linear combination. Let us note, for example, that a subset U of V is a vector subspace if and only if any linear combination of vectors of U belongs to U, namely, U is a subspace of V if and only if for any V1 Vn in U and any alpha 1 alpha n in K, the linear combination alpha 1 V1 plus alpha 2 V2 plus alpha n Vn belongs to U. It is proved that it is enough to verify the statement only for n equal to, which we must admit is much simpler. U is a subspace of V if and only if for any V and W in U, for any alpha beta in K, the combination alpha V plus alpha V plus beta W are in U, is in U. And now some examples of linear subspaces. 1. For an arbitrary linear space V with 0 the null vector, the neutral element of vector setting, U equals 0 and V itself are subspaces of V called trivial subspaces. 2. For V equal R at n, U equal x1, x2, xk, 0, 0. For any x1, x2, xk in R is a subspace of R at n. 3. For V equal R3, U equal 2 x1 plus x2, x1 minus 3 x2, 3 x1 minus 2 x2 for any x1, x2 in R is a subspace of R3. 4. The set of all my shirts is a subspace of my luggage. 5. For V equal Rn, all subspaces have the following structure: U equals sum from I equal 1 to n from alpha I xi, sum from I equal 1 to n from beta I xi, and so on, where alpha, beta, gamma, I are real numbers, not necessary, non-null. Another problem now appears. Consider the subspace U equal 2a plus b, a minus 3b, a plus b, where a, b are in R of R3. We can find a lot of vectors of this subspace simply giving values to a and b. We have therefore v1 equal 3 minus 2, 2, for a equal 1 and b equal 1. v2 equal 4, 2, 2, for a equal 2 and b 0. v3 equal 5 minus 22, 6, for a equal minus 1, b equal 7. v4 equal 9.28 minus 5.86, 6.14, for a equal p and b equal 3. And the show can continue. So, we have an infinity of vectors in this subspace. Is there any way that this infinity of vectors can be reduced to something smaller? The answer is yes. But how do you do? Considering an arbitrary vector of u, v equal 2a plus b, a minus 3b, a plus b, where a, b are in R, we can write v equal 2a plus b, a minus 3b, a plus b equal 2a, a plus b minus 3b, b equal a multiplied by a fixed vector 2, 1, 1 plus b multiplied by again a fixed vector 1 minus 3, 1. If we note now v1 equal 2, 1, 1, v2 equal 1 minus 3, 1, we will have v equal a v1 plus b v2. As a result of this, U is the set of all a v1 plus b v2, where ab belongs to R. Spanning sets of vectors. Being given a vector space V, we will call a spanning set of vectors for V a set S equal v1, v2, vn, with the property that any vector of V can be written as linear combination of vectors from S. V equal alpha 1 v1 plus alpha 2 v2 plus alpha n vn, where alpha 1, alpha 2, alpha n belongs to R, and for any v in V. In the previous example, the vectors 2, 1, 1 and 1 minus 3, 1 are a spanning set of vectors for U. Returning to that example, we can see that the vector v equal 2a plus b, a minus 3b, a plus b, can be written also as v equal 2a plus b, a minus 3b, a plus b equal a multiplied by 2, 1, 1 plus b multiplied by 1, 0, 1 plus b also multiplied by 0 minus 3, 0 for any b, a and b in R. We can see from this that the right mode for a vector v is not unique. It can also easily be seen that any vector space V is a spanning set for itself, taking S equal V. Linear dependence and linear independence of vectors. Being given a vector space V, a set S equal v1, vn, v2, vn, of vectors from V is called linear independent if from the combination alpha 1 v1 plus alpha 2 v2 plus alpha n vn equals 0, if this combination is true if and only if alpha 1, alpha 2, alpha n are all 0. Being given a vector space V, a set S equal v1, v2, vn of vectors from V is called linear dependent if there exists alpha 1, alpha 2, alpha n in R, not all null, such that alpha 1 v1 plus alpha 2 v2 plus alpha n vn equals 0. From the definition of the linear dependent system, it is observed that there is at least one vector vk which can be written as a linear combination of others, so it does not bring virtually anything new. Vk equal alpha 1 v1 plus alpha k minus 1 vk minus 1 plus alpha k plus 1 vk plus 1 plus alpha n vn. Basis. Being given a vector space V, a set B equal v1, v2, vn of vectors from V is called basis if it is spanning set and linear independent. It turns out that having a basis B equal v1, v2, vn for V, any vector V is written as a unique linear combination of vectors from B. For any V in V, there are unique alpha 1, alpha 2, alpha n in R, such that V equal alpha 1 v1 plus alpha 2 v2 plus alpha n vn. The numbers alpha 1, alpha 2, alpha n in R, such that V equal alpha 1 v1 plus alpha 2 v2 plus alpha n vn are called the coordinates of vector v in basis b, and we can write vb equal alpha 1, alpha 2, alpha n. The final headage. 1. Any vector space has a basis. 2. Any bases have the same number of vectors. 3. The number of vectors of an arbitrary basis is called the dimension of the vector space, and we note dim v. Examples. The dimension of matrices with m rows and n columns over R equal m multiplied by n. The dimension of Rn Rnx, the space of polynomials with degree less than or equal with n, is n plus 1. The dimension at Rn equal n. The dimension of the trivial space E equal 1. 4. From the point of view of vector spaces, those who have the same dimension are identical, called isomorphic. Wow, it's over. Thank you for your attention.